A sequence has a0 equals 3, and then for n greater than or equal to 1, the sequence satisfies an is equal to 8, an minus 1 to the 4. The value of a10 is one of these values. Okay, so the first thought that comes to my head for trying to solve this is to write out the first few values of an. So we have a0, could easily write a1, a2, a3, and see if we can figure out the pattern. That might just be the most straightforward way to do this. Typically, I like to try and figure out something a little bit more elegant. But yeah, if I want to see what the pattern is, I think this will probably be, a0 is equal to 3. We could even try to solve for the general term an, and then just substitute n is equal to 10. But solving a recursive, an, I want to write down the general term. Solving for the recursive sequence for the general term sometimes is most easily done by writing down the first few values. So a0 is equal to 3, a1 is equal to 8 times 3 to the 4, a2 is equal to 8 times 8 times 3 to the 4 to the 4. So if I write this as a1 is equal to 2 to the 3 times 3 to the 4, that's equal to 2 times 3 to the 4 divided by 2. Which is 6 to the 4 over 2. So then a2 is equal to 8 times 6 to the 4 over 2 to the power of 4. I mean, based on looking at the answers, well, why don't we try and simplify this then? This is equal to 2 to the 3 times 6 to the 16 divided by 2 to the 4, which is 6 to the 16 over 2. And then a3 is 8 times 6 to the 16 over 2 all to the 4. So that's, again, 2 to the 3 times 6 to the power of 4 times 16. Divided by 2. 6 to the 4 times 16 over 2. So it looks like well, hold on. 4 times 16 is 64. So it looks like an is equal to 2, 2 to the power of 2n over 2. Sorry, not 2, 6. And let's see if we can. So in this case, the answer is 6 to the power of 2 to the 20 over 2, which is option E. But let's try and show that this is the general solution. So pretty much exactly what I said happened here, in that I wrote out the first few terms, and then I believe I have identified what the pattern is. I was helped a little bit by the form that the answers were written. So, you know, I guess I had a bit of a hint going into this. But if an is equal to that general term, if we assume that that's true, I mean, it certainly matches a0 is equal to 6, 2 to the 0 over 2. That's equal to 6 to the 1 over 2, which is equal to 3. So that works. And now we just have to show that this satisfies the recursion. So an plus 1 would be equal to 6 to the 2 to the 2n plus 1 divided by 2. That's equal to 6 to the 2 to the 2n plus 1 divided by 2. 6 to the 2 to 2n times 2 divided by 2. Hold on a second. It doesn't seem to... Oh. No, I think we're okay. I want to write this as... just a minute. How do I want to write this? I mixed up an exponential. I must have screwed up an exponential rule somewhere. Or it wasn't even an exponential rule, it was a standard simple multiplication. This is a 2n plus 2 here. So that's 6 to the 2 to the 2n times 4 divided by 2. 6, 2 to the 2n times 6 to the 4 divided by 2. Maybe it's best not to do it this way, but to write 6 to the 2 to the 2n to the power of 4. And then this is all divided by 2, but I'll raise that to the power of 4 and multiply by 2 to the 3 here. And here I get 8 times 6 to the 2 to the 2n over 2 to the power of 4, which is what I want. So I've shown that the general expression here, I've shown that this satisfies the recursion that we started with. So I have the general solution now, and I can then just, of course, read off let n equal to 10. And we do, in fact, get this. But I basically just, you know, the way I went about this originally, rather than solving for the recursion. I mean, I did solve for the recursion, but I didn't prove it. I just followed the pattern as best as I could. And we got the answer like that. But yeah, nice little problem. Probably could have gone about this a little bit quicker. But if I have a mistake, I'll let you know. Thanks for watching.